Hey, what's up everyone? It's Jake from Algo Daily here, and today we're going to cover this tutorial, an executable data structures cheat sheet for interviews. So what we're going to do is we're going to go through each of the 9 most important data structures for technical interviews, and I'm going to do this using the Algo Daily interactive platform. So the goal of this is to get you more familiar with the building blocks of a lot of the algorithmic solutions that you're going to solve and encounter uh, during the course, and help you prepare for technical interviews by getting you familiar with these data structures. This is also a good opportunity to explore the benefits of using an interactive platform like Algo Dailies, where you can execute code and see visuals to help you speed up the learning process. So, without further ado, let's jump into arrays. Now, this is an array, so we have elements and indices. Notice that the indices start at 0 and go up to 3. In this specific example, we're talking about static sized arrays, which are found in a lot of the statically typed programming languages. So we call an array a collection that stores elements in order and looks them up by index. So we have index 0, 1, 2, 3. Indexes start at 0 and continue counting up. This is the most important thing. For arrays of many languages, they're of fixed size. So when you instantiate an array in JavaScript, notice that we don't have to give it a size. In JavaScript, the size of an array is dynamically allocated, so we can always push elements to an array without worrying about going over the size constraints. With this one, we really have to be careful, because with static arrays in many static languages, you do have to provide a size at the very beginning in order to know how big the array is going to be. Another thing to keep in mind is that arrays store elements sequentially, one after another, and it allocates contiguous memory space for all of its elements, meaning that all of its elements can be quickly accessed because they're stored right next to each other in memory. And so the pros of using an array is that there's constant time access by index. So let's look at this example over here. We initiate an array. We initiate an array with teams, so Knicks, Mets, Giants. And then with literal notation, we can also instantiate Nets, Patriots, Jets. And then we can use any of these methods to access properties and parts of the array. And if we click run code, we can see that in this example, we gave it the index of 0, and we immediately got back Knicks. And it's able to do so really quickly because it knows where every element is, because they're right next to each other in memory. So there's constant time access by index, but there's also constant time append. Because an array of a fixed size doesn't change its size unless specified, we always know where the end of the array is going to be. And as a result, if we know where the end is going to be at all times, we can just plop the new element at the end of that array. Now, some cons. It's a fixed size, so it can't be changed unless specified. Search, insertion, and deletion are O of n, because if you ever want to search an array or insert or delete elements in the middle, you're going to have to iterate until you get to that point and then insert or delete elements within the array. And of course, another con is that it can be memory intensive when the capacity is underused. So if we allocate an array with 1,000 elements that are supported, and we only use up two slots per se, or we only push 2 elements, then we're wasting 998 elements worth of space in memory. Some notable uses are the string data type in many programming languages. It's actually represented by text that comprise of arrays involving one character each in each slot. And finally, let's go through the time complexity quickly. So access is O of 1, so it's constant time. Search, insertion, and deletion are O of n. And just one last thing to note is that you can also have multi-dimensional arrays. So something like this is totally fair game. Now, let's move on to dynamic arrays. In JavaScript and Python and other dynamic languages, an array is already a dynamic array, so we'll just cover the differences. In short summary, a dynamic array is an array that can resize itself. It's also known as an array list, growable array, resizable array, mutable array, or a dynamic table. Some important facts. So again, similar to static arrays, it stores elements sequentially using numeric indexing and allocates contiguous memory in space. So same as before, everything is right next to each other in memory, so you don't have to worry about speed, and the access pattern is still pass an index and you get the element back. The difference is that a dynamic array expands as you add more elements, and it doesn't require setting initial capacity. So in this example, if we were to have this teams array, and we do teams.push algo daily, and let's say here we console.log teams out, it gets pushed. We don't have to specify an initial size or worry about size constraints. When a dynamic array exhausts capacity or it runs out of space, it allocates a new contiguous memory space that's double the previous capacity in most cases, and copies all values to the new location. And the time complexity is the same as for a fixed array, except for worst case appends. So when capacity is doubled, append is linear time, O of n, because we need to iterate through all of the elements to know where the end of the array is in order to append it at the very end. But the average append is still O of 1 constant time due to the sizing of most dynamic arrays. So the pros of dynamic arrays: variable size, it expands as is needed, and we don't have the need to specify size up front or worry about the sizing constraints, and it's still constant time access. The cons are worst case appends are linear time instead of constant, and insertion and deletion are still a bit slow relative to appending. So as a workaround for static fixed size arrays, there's also linked lists. With linked lists, you can think of it as nodes that are attached to each other via this next property. So what is a node? A node is just an element within this list that contains some information. The first node is called the head in a linked list, and the last node is called the tail in a linked list. So in each of these nodes, there is some data that's contained within the node and what we call a pointer of the node. The pointer of the node connects this node to another node, and the list is created when each of these nodes is connected and thought of as an aggregate. So a quick summary is a linked list is a linear collection of elements ordered by links instead of physical placement in memory. There's a few types of linked lists. There's a singly linked list, which where each node stores a reference only to the next node. So this is an example of a singly linked list. In a doubly linked list, each node stores references to both the next and previous nodes. So imagine if this guy points to this guy, but also this guy were to point to this guy. That would be a doubly linked list. In a circularly linked list, the tail, we have our tail right here, stores a reference to the head. So this guy would point to this guy at the very beginning. And one more thing to note is that stacks and queues, which we're going to cover in a bit, are actually often implemented using linked lists, and less often using arrays due to the flexible nature of linked lists. So here we have an example in JavaScript. We have a linked list node, which is just a function representing an object that contains the value and a pointer. And when we construct a linked list, we have a head and tail. And then to append and prepend nodes, let's just cover append. We create a new linked list node and either stick it at the beginning, or if there's already an existing head, we stick it to the end of the tail. So this .tail would refer to an existing node, and we would take our new linked list node and stick it at the end of that tail. So pros, linked lists are great for fast operations on both ends because we have pointers to both ends, and it ensures constant time insertion and deletion. And it's flexible. Like dynamic arrays, it doesn't require setting initial capacity and can be expanded indefinitely. The cons are, it's expensive to access and search. In order to access a node, you have to start at the head, usually, and go to where the node is to get it back and retrieve the contents. Same with searching. You have to iterate through each of the nodes in order to get to the one you want. Additionally, they don't occupy, linked list nodes don't occupy continuous memory locations, meaning that the node values and data stored in memory isn't guaranteed to be right next to each other or in close proximity to each other, so it's a little bit slower than iterating through an array. Time complexity, access and search are linear time complexity, and insertion and deletion are constant time complexity. And if we run this code, we can see that we start off at the bottom here. We initiate a linked list class. We append 25, 15, 5, and 9. Or sorry, we prepend these guys. We prepend 25, 15, 5, and 9. And so you can see that these pointers open up correspondingly. And at the very head, 9 contains a pointer to 5, contains a pointer to 15, contains a pointer to 25. Now let's cover queues and stacks. So you can imagine a queue as another list where there's an entry point and then there's an exit point, or what we call an enqueue point and a dequeue point. So imagine you're going to the bank and you're waiting for a teller. The queue is just a line that you wait on to get access to service. So for this queue, if the teller was over here, the teller was E, and we get on line A, we're guaranteed to wait in line until something occurs here. Now queues are very helpful because it helps us keep an order for elements, or in real world use cases, events, or some other thing that we're tracking. It makes sure that things happen in a sequential nature as expected. So a quick summary is a queue is a sequential collection where elements are added at one end and removed or operated on at the other end. So some important facts. It's modeled after a real-life queue, and we call it first come, first served. The more popular terminology is FIFO, which is first in, first out. And similar to a linked list, the last added node is called the tail, and the final node is called the head. So here it's the head, and here it's the tail. So two fundamental operations are enqueuing and dequeuing. These are the more important things for the API, if you will. And we've implemented it in our queue structure and queue class on the right. So enqueue simply inserts it at the tail of the linked list. In our case, we've implemented it with just an array, but you can also implement it with a linked list. So enqueuing just means to put it at the end and have it get ready to be on the line. To dequeue means to pop it off the start and do something with it. So the goal is just to get A through this series and to allow it to get to this point. We've already covered that it can be implemented on top of linked lists or arrays. And pros are constant time insertion and deletion. So we always know where the tail and head are, so we can always add elements and remove them quickly. And access and search are O of n linear time because we need to iterate and find the element within the queue. Some notable use cases are CPU and disk scheduling, interrupt handling, and buffering. So anything that requires keeping track of events that are happening and making sure they occur in sequential order can find use in having a queue. In terms of time complexity, access and search are linear time, and inserting and deleting are constant time. Now, with a stack is essentially a queue, except the order of operations is a little bit different. So with a stack, you can think of an actual paper stack where you put stuff on, and the last thing you put on is going to be the first thing that you pop off. So a queue, the terminology is a sequential collection where elements are added to and removed from the same end. So when I push in terms of the order of elements that go in the queue, we pushed A, then we pushed B, then we pushed C. But when we remove elements from the stack, we're going to remove C first, and then B, and then A. So important facts, it's first in, last out, or FILO. And it's equivalent to a real life, think of it as a pile of papers on a desk. The two biggest operations or APIs are the push method, where we push items onto a stack. So whether we implement it with an array or a linked list, push just puts it on the stack. So when we push items to the end of the array. And then when we pop items, we also pop items not from the start of the array, but from the end of the array as well. And it's often implemented on top of a linked list, even though in this example, we're implementing it on an array. Pros, fast insertions and deletions, similar to queues. Access and search are O of n, linear time. And so imagine the use cases of having a stack. You can maintain your undo history because you pop things, you push things onto the stack. Imagine browsing several web pages, you're pushing them onto the stack. And when you need to go back, you just pick up the last one that you pushed on. Tracking execution of program calls via a call stack. And reversing an order of items is also easily done with a stack. In terms of time complexity, access and search are both linear time operations because you need to iterate through the elements to get to a certain one. And inserting and deleting are constant time because we always know where the top and bottom of the stack are. Cool, let's cover hash maps now. So hash maps and hash tables go by many different names. They can be called dictionaries in Python, associative arrays in PHP. There's also the map object in JavaScript. So there's a few terms, but ultimately they're all very synonymous with this unordered collection that we have here that maps keys to values using hashing. So here we have a hash map or a hash table where the keys, server, status, xframe options, point to values within the data structure. And you can think of it as the following. You can think of it as the evolution of arrays in the sense that it removes the limitation of sequential numerical indices and allows using flexible keys instead, like server, status, and xframe options. So the way it's implemented is usually using an array or linked lists and a hashing function. Here we have an example of a hashing function that takes in a string and computes the location of the element in storage. And the reason people love using hash maps is because of this. So not only can keys be of many different types, but the average search, insertion, and deletion speeds are usually in constant time. Due to the way it works, if there's an underlying array, we can easily look things up, search for them, or delete them. Now notice that this is the average speed. In worst case, it's still linear time access, search, insertion, and deletion. But for small enough hash maps, you usually get to constant time lookups. And so this is super helpful when we want to deal with looking things up by strings, for example. For any given non-numeric key, hashing, or using the use of this hash function, helps us get a numeric index to look up in the underlying array. And then notice that if there's multiple strings that come out to the same number within the hashing function, this is called a hash collision. And then to mitigate this, instead of storing actual values, there might be a layer in between where the underlying array may hold references to linked lists where the actual values of the hash are stored within the linked list instead. And finally, a set is a variation of a hash table that stores keys but not values. So we've gone over the pros. Lookup speed is super fast, and we can use keys that aren't numeric indices. But the cons are, worst case lookups are still linear time, and not ordering means looking up minimum and maximum values is expensive since there's no sense of order. Everything is stored in the underlying data structure in no specific order. And some notable uses of hash maps are caching, database partitioning, or many other times when you just want to look things up via a string as a key instead of indices. And so here we have an example of a hash map implementation. We start off with an array. We have this hashing function that takes in a string and gets us the index that the element is stored at within the array. And then we set keys with this method, and we get keys with this method. So let's see how this works. Here we initiate a new hash map. We set the key as James and put this phone number in. And we set the key as Jess and put this phone number in. And then when we log out dict.getJames, we get the appropriate number. All right, let's move on to graphs. With graphs, you can think of them as nodes that are connected to each other via vertices. So A, B, C, D, E are all nodes, and they're connected to each other by these lines that are called connections, edges, or links. And using a graph is a great way to express the relationships between different nodes. So a quick summary is a graph is a data structure that stores items in a connected, non-hierarchical network. And so let's go through some terminology real quick. Each graph element is called a node or a vertex and multiple nodes are called vertices. So A, B, C, D, E are all vertices that are connected by edges. Graphs can be directed or undirected, meaning that A can point to B, but B may not necessarily point to A. So a direct graph would have A pointing to B, B pointing to C, but C wouldn't be pointing to B, and B wouldn't be pointing to A. The picture here is one of an undirected graph. Graphs can be cyclic or acyclic. So a cyclic graph contains a path from at least one node back to itself. So here we actually have a cyclic graph because B points to E, which points to D, which points to B. So there's a cycle here. And graphs can be weighted or unweighted, meaning that this connection from B to D might be stronger or worth more than the connection from D to E. So here we have an unweighted graph. And graphs can be traversed. And traversal is just a fancy way of saying that we iterate through the nodes, or we visit all the nodes, or we travel to all the nodes, and do stuff to each of the nodes. And here are some ways that data structures can be used to represent graphs. I won't dive into too much, but each of these is a different way of implementing the relationships between nodes in a graph. On the right, we have an example of an adjacency list representation, which is a list or a hash table where a key represents a node and its value represents the list of its neighbors' nodes. So if we run the sample code, we can see at the bottom here, we instantiate a new graph. We have these vertices and we iterate through each and add the vertices into the graph. So this just sets a hash map, and then in each hash map, it sets a key with the nodes being the key. And then when we add edges, which we do here, what we're doing is in each of the hash map keys, we're actually pushing the relationship directly into the array set for that vertices. And so the representation we get, if we log it out, is actually this. A is connected to G, A is connected to E, and A is connected to C. So A has G, E, and C be its neighbors, and the rest continue as such as well. So pros of a graph, there's so many use cases. Notably, social media networks are represented by graphs. So each person is a node and they're connected to each other through various ways. Recommendations in e-commerce sites and other recommendation engines, and mapping services. So imagine when you're looking at Uber and you can see that you're at a certain destination and your driver is at a certain destination. The representation of that map occurs via a graph. And a pro is that it's ideal for representing entities interconnected with links, but the cons are low performance relative to other data structures makes scaling a bit difficult. But of course, not too difficult to the extent that Google, Uber, and Facebook are all huge graphs that comprise of billions, if not trillions at this point, of entities. And the time complexity depends on the choice of algorithm, but for most things, for most operations, it's O n of log n or slower, depending on the implementation. And what this means is that essentially you have to often iterate through the number of nodes at the very least to do the action that you want. Let's move on to trees. So trees are actually a type of graph. A tree is a kind of graph where between any two nodes, there's only one possible path. So picture a file directory. The file directory at its root may have a folder called content. There might be two subfolders called assets and blog. And then under assets, there might be two files. And under blog, there might be three more folders. And so that's a tree representation. And it's great for hierarchy. Notice that content is at the very top. And so we know that it's a parent. And that's really helpful when we need to organize values hierarchically. Similar to a graph, each tree node is called a node. And every node is connected to 0 or more child nodes using links or edges. And then the top node is called the root. And the bottom nodes that don't have any more children are called leaves. So icon, sprite, 2020, 2019, 2018 are all leaves. And content is the root. The number of links from the root to a node is called the depth. So 1, 2, 3, the depth here is 3. And the height of a tree is the number of links from its root to the furthest leaf. So 1 link, 2 links, so the height is 2. In binary trees, which are a special type of trees, nodes can't have more than more than 2 children. Any node can be a left or right child. And binary trees are used to make binary search trees, which we're going to cover in a bit. Trees can usually be traversed in 2 different ways: breadth first search and depth first search. Without going too deep, breadth first search is going level by level. So we would go to content first, then we would go to assets and blog, then we would go to icon, sprite, 2020, 2019, 2018. Depth first search would have us going content, assets, icon, then sprite, then back to content, then to blog, then to 2020, then to 2019, then to 2018. So we're going deep first and then going level by level. So the pros of using a tree is that for most operations, the average time complexity is O log of n, which enables solid scalability. Worst time complexity varies between O of log of n and linear time. The cons: performance degrades as trees lose balance, and rebalancing, which we won't cover here, but there's tons on Algo Daily about it, requires effort. And there's no constant time operations because you typically need to iterate through the nodes of a tree in order to perform an action. So notable uses, as we covered: file systems, database indexing, syntax trees, and comment threads. So here on the right is one way to represent a tree, which is by focusing on the tree nodes. We have a function, tree nodes, that contains a value, a potential array for children, and potentially a parent. And we set each of these properties via setter methods, and they build relationships on each other. So if we scroll down to the bottom here, we see that we instantiate a tree node with a value of 1. Then we add a node 2 and 3. And then what we do is we get the children for the root, which are 2 and 3. And then we iterate through the children And then for each of those children, we add more children. And if we console log that guy out, let's see what we get. We get the tree node, which is 1. It has a child. It has 2 children, 2 and 3. And then each of them have children as well. And so we can continue for a bit, but that's the main idea. Now, finally, onto a special kind of a tree called binary search tree. Now, binary search trees are a kind of binary tree, meaning that each node only has 2 children, where nodes to the left are smaller and nodes to the right are larger than the current node. And it's called a search tree because it's super fast to search. Pros: balanced binary search trees are moderately performant for all operations, but since it's sorted and ordered, reading its nodes in sorted order can be done in O of n linear time, and search for the closest node in value can be done in O of log of n time. And so binary search trees look like this. You may have a root node that then has 2 children, where the left child is smaller than the parent, and the right child is larger than the parent. Same as you go down, the left child is smaller than the parent, and the right child is larger than the parent. And so that means if we're looking for specific properties and specific values, it's quite easy because we can do comparisons. If we're looking for nodes that are smaller, we just go left. If we need to find nodes that are bigger, we just go right. So because nodes of a binary search tree are ordered in a specific way, all nodes to the left are smaller, all nodes to the right are bigger than the current node, and duplicate nodes are usually not allowed. Some downfalls are that there's no constant time operations, and performance degradation in unbalanced trees occurs. It's about linear time for all time complexities in the worst case, and log of n in the average case. And here we have a representation of a node in a different style. So we have value, left, and right, since that's all a binary search tree node can contain. And then when we add a node, there's some additional logic that we have to do in order to find the proper positioning. Because if we look at this find position and insert method, we need to compare it against the nodes and traverse through the rest of the tree to find out the proper place to put the node based on its value. So we look at the current node and compare it to the new node. If it's smaller, we go left and we recursively continue. If it's larger, we go right and we recursively continue. And removal has its own set of problems because we need to also continue to compare values to know where to put the new node, and then once the new node, or where to remove the new node, and once the node that we want to remove is gone, we have to figure out what should be in its place, if anything. So here is an example where we instantiate a binary search tree with 4. We add 3 and 5. And if we look, the value at the root is then 4. And at its left node, oops, let me comment this out. So at its left node, we have 3. At its right node, we had 5. And then if we were to remove 3, then we get 5, which is still on the right, but nothing on the left. All right, that's 9 data structures. Thank you so much for watching, and I hope this was helpful.